In reinforcement learning, an agent gets ambiguous feedback in the form of a reward. The agent must find its own way to a strategy which maximizes expected reward. You might think that a perfectly rational reward-pursuing agent would narrowly focus its efforts on success, exploiting only true causal relationships. If you thought that way, you'd be wrong. This is Data Skeptic Consensus, and the 27th installment in our series about how multi-agent systems achieve collective decision-making. Hal Ashton joins me today to discuss his research demonstrating particular emergent behaviors in some of these agents that are a bit like superstition. It seems reinforcement learning is not immune to cognitive errors.
My name is Hal Ashton. I'm a PhD student at the University College London. My main topic of research is market manipulation. If you have a self-taught trading algorithm, does it learn to manipulate markets? And then going on from that, how do you stop it from manipulating the market? And kind of more generally, how do you tell an algorithm which learns a policy, how do you tell it that certain things are illegal and shouldn't be done? So it's kind of taken me on a more circuitous journey than I thought it would, because I've gone into the world of experimental psychology and law, because a lot of market abuse laws are very interested in intent, criminal intent, and they're also interested in causality. My work at the moment is trying to establish what intent looks like for an algorithm, and the work that we're going to be talking about today is connected to causality. So this wasn't an area that really came up in my kind of formal machine learning education, and it was only probably just over a year ago when I read a book by Judea Pearl called The Book of Why. I really started getting interested in the subject of causality and realised that it's something that isn't taught and it isn't handled well in machine learning at all. And if you read the book, Pearl is very adamant about the importance of causality and how certain types of analysis simply can't work without taking causality into account. So it drew a question in my mind as to why or how certain machine learning techniques like reinforcement learning work when there's no explicit treatment of causality at all. So that led to the dog barometer paper, which I call it, but I think formally it's called Causal Campbell-Goodhart's Law in Reinforcement Learning. So reinforcement learning should be all about causality. You have an agent, he chooses actions, they choose actions, that somehow changes the world, they receive some kind of reward, the world changes, and so it goes on. So you would think that reinforcement learning and causality go well together. And actually, if you were to believe Pearl that they can't work, reinforcement learning shouldn't be able to work if causality isn't explicitly treated. But if you look at Sutton and Bartow, which is the canonical text on reinforcement learning, if you do a search for the word causality, causal, anything like that, it appears exactly 0 times in the entire book. So someone's got to be wrong. Either Pearl is wrong in saying that causality is absolutely key when you kind of generate any kind of policy to solve a problem, or reinforcement learning has just got extremely lucky so far in that the questions that they've studied haven't contained any kind of interesting causal structure.
I agree that the word causality is suspiciously missing from most of the reinforcement literature, books, and papers I've encountered, but it almost feels like it could be there implicitly. Could this just be a matter of semantics?
Well, that's the great hope from deep reinforcement learning, I guess, that you somehow, by involving a deep neural network in all of this, somehow in that deep neural network, which is unknowable and mysterious, it does the job of analysing causality for you. It does it automatically, so you don't need to think about it, and it's done. You don't need to worry about it. Reinforcement learning works, so let's move on. And I guess there is an element of that, because reinforcement learning does work, but it just kind of made me think about, if you look in science in general, there's a long history of humans discovering techniques which work before actually understanding why they work. So I was thinking about iron. The Iron Age was 500 BC, even slightly earlier. And to make iron, you need to take iron ore, you smelt it with coke, and the coke burns in the air, that produces carbon monoxide. The carbon monoxide then displaces the oxide in the iron oxide, which then leaves you with raw iron. So at what point in human science did we realise that was happening? Probably 2,000 years later, maybe 1800s. All this time we still had iron tools, so it didn't really matter that we didn't know why it worked. Did kind of work. And I kind of liken that a bit to reinforcement learning, maybe, that you have a process which does work. It's a bit mysterious. Maybe you've got to do certain things to get it to work, but the actual understanding as to why it works isn't there yet. And I think without an understanding of causality, we can't really understand why reinforcement learning works.
I can pull out a textbook or maybe go on GitHub and find some source code. And, for a reinforcement learning problem, I can, as a programmer, I can read those lines and tell you what it's doing and even verify the arithmetic calculations it does. So in some sense, I understand how it works. What's the difference between my version of understanding and yours?
I mean, firstly, if you look at the canonical success examples of RL, they are in computer games. And in computer games, the relationship between your action choice and the kind of causal effect of your action choice is very clear. So you press up on your joystick and your Pac-Man moves up, or you press left and it goes left. But in the real world, the impact of your action is not always obvious, and there's hidden variables involved. So it might just be that the success cases of RL are in simple kind of causal examples where everything is very much visible. And the causal effects are quite simple. And that is the case with basic computer games and Go as well. In AlphaGo, it chooses a position to play its counter, and the counter appears there. There's no uncertainty as to whether it does appear there or not. It's completely visible. But when you start porting reinforcement learning into real-life scenarios, this 100% correspondence between action and effect doesn't translate across. So an example is, my area of study is trading. So if you want to train a trading algorithm using reinforcement learning, then all of a sudden you have a whole slew of unobservable variables, which you're never going to be able to observe. So you're never going to know what trading positions are of other traders in the market, for example. And that's something that's very different from the kind of lab uses of RL.
If I were to be a reinforcement learning apologist, I guess some of the things I might point out is, there are mechanisms for dealing with delayed rewards or hidden variables. Perhaps I could have a belief about that value of the hidden variable and update my belief in some Bayesian way and be able to kind of take good probabilistic actions. And certainly those techniques do work. Are those necessary but not sufficient, or how would you characterize the current state?
I would say they are quite complicated to understand why they work exactly. And the aim of my paper was to kind of check out, using a very, very simple causal example, to check out a number of kind of common implementations of deep RL and see whether they cope. And the hope is that when you use a toy model, you can easily see what's going wrong if something does go wrong. So my example, it's about a dog that lives in Scotland, and the weather in Scotland is either sunny or it's rainy. And the dog likes going for a walk, as all dogs do, but it would like to be dressed in the appropriate way of the weather. So it can wear a coat if it's raining, or it can not wear a coat if it's sunny. If it's wearing a coat and it's sunny, that's a bad outcome. And if it's raining and it doesn't wear a coat, that's a bad outcome. So the dog's in his house, and luckily he has a barometer. The barometer measures the pressure at any time. The pressure is a good predictor for weather the next period when he goes for a walk. So this is a very simple RL game, which I was able to program into OpenAI's gym environment. The other option that the dog has is to press the barometer. And by pressing the barometer, it sets the barometer to a high reading, which in the normal way would indicate high pressure, which would indicate sunny weather for going for a walk. So the paper just investigates whether, if you use two deep RL standard algorithms, whether the stupid naive policy comes out or whether the clever policy comes out. The stupid policy being the dog presses the barometer to cause the pressure reading to be high, so therefore it will think that the weather in the next period will be sunny, so it can go outside without its coat. And that's a very simple problem that as humans we intuitively understand, that there's no causal mechanism between the barometer and weather. It works one way only. So the barometer is an indicator of weather, but you can't change the weather by manipulating the barometer. So this is simple and intuitive for humans, and I think as humans we understand this causal relationship quite early on. But for a neural network, for AI, for RL, it's an open question as to whether that relationship is understood at all and how it is understood. So looking through the existing research on this, there was nothing really which kind of justified this paper and the very simple model. The results of the model were, I guess I'll call it a draw for the RL guys and for the causal guys. So one of the algorithms succeeded very well in kind of ignoring the fact that a dog could press the barometer, and in fact he should just look at the barometer, not try and manipulate it, and then go out with or without the coat depending on the barometer reading. And the other algorithm, which was DQN, which is a deep variant of Q-learning, that was the one that failed miserably. And that was the one that told the dog to press the barometer if it had a low reading so that it could make a high reading. So therefore it would make it sunny. Now, the two algorithms are, as it happens, of two different techniques in RL. So one of them is a off-policy learning algorithm. One of them is an on-policy learning algorithm. So the one that succeeded is the on-policy algorithm. So that's the one that it learns by choosing a policy, then following that policy, evaluating it at the end of it, and then kind of adjusting the policy. So the thing that's important here is that it will understand that pressing the barometer is in any policy doesn't really affect the outcome. That was A2C. And that's been proven. It's a successor of DQN, actually. It came out a few years later, and it's proven to be superior in a number of ways. Using that method, we return a perfect answer, which is don't bother pressing the barometer, just read it, and then wear your coat depending on the reading. So the other one is where it gets a bit more interesting, is DQN. DQN is off-policy learning, so it never actually assesses a whole policy before kind of changing the policy. What it does is it pulls data together, which is gathered through kind of random experiences, and then it tries to recover an optimal policy from that. And this is where you get to the nub of the matter as to why it fails. Because when it gathers its policy together, it fails to distinguish between the cases when the dog did press the barometer, and it fails to distinguish the cases where it didn't. So it just kind of mixes them up together. And when it comes to recovering a kind of optimal policy, because it mixes these two settings together, it recovers the policy where it says that you should press the barometer. I mean, this is interesting in itself because it says, the result says that your RL approach is going to be more robust to kind of causal errors if it is on policy, an on-policy learning method. That was not pointed out in literature before. There are methods to debias DQN. So people have noticed that there are problems with DQN in this caching of data together generator under different policies. And they've come up with a number of algorithms which based on importance sampling. So they try and kind of correct for the fact that the data was generated under different policies. But if you actually look through the papers, it's quite hard to understand what they're doing exactly. If you interpret it from a causal scientist point of view, it's very easy to see why DQN has this causal error tendency. I think in terms of kind of teaching aid, it really helps kind of looking through this causal lens to see why DQN fails.
I was hoping we could break down a little bit of the problem. I know you're using an MDP, a Markov decision process, which is defined by a very convenient tuple. Even for listeners who don't know it, I think it's helpful to kind of just walk through the setup. Would you mind telling us a little bit about the states and actions and such?
So in terms of states for the model, there is a pressure state, which pressure is the predictor for weather. There's a weather state, so the weather is only dependent on pressure in the previous period. And then there's a barometer state, so the barometer state is only dependent on pressure. So you can kind of represent this in a nice simple causal diagram where arrows between nodes denote a causal relationship, a one-way causal relationship. So first off, you can have the pressure variables. So P0, your pressure at the first period, an arrow going to P1, and then an arrow going to P2. And then if you imagine arrows moving upwards from the pressure variables up to the barometer variables, an arrow from action variables moving into the barometer variables, and then an arrow moving from pressure into the weather variables. There are 4 different actions that the dog can choose. The dog can wait for the next period without doing anything. It can press the barometer. If it presses the barometer, then the barometer gets set to a high setting next period. It can also leave the house with a coat, and it can leave the house without a coat. And when it leaves the house, the game ends. That's the simple setup. In terms of rewards, the dog gets rewarded the most if it goes out in sunny weather without a coat. It gets a little less reward if it goes out in rainy weather with a coat, and it gets heavily penalised if it's just not dressed appropriately. So if it's wearing a coat and it's sunny, or if it's not wearing a coat and it's rainy.
Gotcha. Well, it seems like a good setup where I would hope we might see some behaviors like, first of all, the dog learning to ignore the button, maybe even the dog learning to take advantage of weight if they determine from the measurement that it's raining out. And as you said, going out rainy with a coat, that's rewarding, but even better is sunny with no coat. And if I somehow figured out it's raining now and is going to get sunny, perhaps depending on the reward structure, I should wait. These are the things we'd like to achieve, I guess. Did you expect those behaviors going in, or did you think something else would come out of it initially?
I was kind of neutral as to what my expectations were. I changed the pressure setting. So originally pressure is non-correlated. So it's just a random walk. It switches between high pressure and low pressure. There's no particular relationship. And in a second experiment, I tried a kind of correlation. So if pressure was high last period, then it probably will be high this period. In the first setting, I guess kind of intuitively you would expect weighting. So given that it gets rewarded more for sunny weather, if the pressure reading is low at the moment, it could probably wait for a bit for the pressure to go up to a higher level. So it's probably going to be sunny the period after that, so it would go out without the coat. Once you have this autocorrelation of pressure, then the weighting strategy becomes a little less rewarding because you could be stuck in a low pressure for a while, which is actually slightly more realistic of English and Scottish weather. If you're waiting for it to be sunny, you might have to wait a number of days. I was actually kind of thinking that given the neural networks that I gave it, I think there were 64 neuron, 2-layer networks, I was expecting the optimal strategies to be returned each time. And the fact that they didn't for one of the learning methods was surprising. And it's not only that they didn't, they would consistently not return. So DKN would consistently return the naive policy 10 out of 10 times.
Can we talk for a moment about maybe the engineering side of it? What does it take to go from this interesting problem setup to a software that computes a policy for you and how you run these tests?
I spent a long time on previous projects faithfully looking through papers and then coding up the algorithms that we present in the papers. And that's great for personal development. It's good for coding. It's good for understanding why the algorithms work, how they work.
Good for having bugs, too.
Yes. On the flip side, if you code something yourself, especially these algorithms which are quite finicky, if you code them yourself, there's a high chance that you're introducing bugs in them. And the bugs that you're introducing into them aren't necessarily easy to find. So having had that experience and learned from it and felt that I'd got enough learning experience from programming myself, I found there's a package in Python called Stable Baselines where someone else does the programming of these deep learning algorithms. So for a kind of scientific endeavor where our objective is not to develop new learning algorithms, it's just to say it's something else, this kind of package is invaluable because it saves an enormous amount of time. It makes your work repeatable, and it also kind of eliminates some of the risk of a bug being in there, kind of invalidating your results. So I would say to anyone getting going in RL, reinforcement learning, that to use someone else's implementation of these learning algorithms is highly recommended because it will save you so much time debugging.
Thanks to this week's sponsor, LinkedIn Jobs. 2021 is looking up. New beginnings means new opportunities to grow your business. If part of your strategy is adding new members to your team, LinkedIn Jobs finds the right person quickly. And to get you started, Data Skeptic listeners get to post their first job for free. Nothing to lose, cast a net and see what kind of talent comes back. I've used LinkedIn Jobs on both sides of the table and enjoyed it very much. As a hiring manager, what was great was getting a compact list of people who applied and being able to open every candidate in a different tab and kind of cycle down to the best few that I wanted to go on to the next step with. Hiring anybody is a multi-step process, but step one is sites like LinkedIn Jobs. And what I personally found there that I didn't see everywhere else was a high enough volume of good quality candidates. You can get high volume, but not necessarily the sweet spot of volume and quality. So how does LinkedIn Jobs help you find the right candidate? First off, it's an active community of professionals with more than 722 million members worldwide. Getting started is easier than ever with new features to help you find qualified candidates quickly. Post a job with targeted screening questions and LinkedIn will quickly get your role in front of more qualified candidates. You can manage your job posts and contact candidates all from a single view that's familiar to anyone who's used LinkedIn before. And whether you're on a desktop or a mobile device, it's going to work great either way. So when your business is ready to make the next hire, find the right person with LinkedIn Jobs. Data Skeptic listeners get to post a job for free. Just head over to linkedin.com/dataskeptic. Again, that's linkedin.com/dataskeptic, all one word. That link will allow you to post a job for free. Terms and conditions may apply. And when you run with those, so you have a way of formalizing the problem and the way that that algorithm understands, what does it give you back? What does that policy actually look like in bits?
I mean, the other element as well is that reinforcement learning implementations, I mentioned it before, there's an environment called OpenAI PyGym. So if you program your problem set up in the specific way that that environment works and expects, then you can plug it directly into stable baselines. That saves time as well. The output from stable baselines will be a trained neural network. So then it's up to you to try and kind of retrieve from that neural network what's going on. So you can just exhaustively in this case, because we only have a very small state space, we've just got pressure, the barometer, the weather state, we can kind of exhaustively go through all of the initial states and then kind of retrieve what the policies that this neural network generates as a result. So as a result of choosing a very simple toy model at the beginning, we're able to interpret this trained neural network at the end and kind of exhaustively work out all of the possibilities of the policy that it generates. This is an advantage of the toy model, and it's a disadvantage of using deep neural networks for real life problems as well, because if you have a very, very complicated problem and you come out, your output is a neural network black box, how, say, as a risk manager, would you ever become confident that, e.g., your trading algorithm, it doesn't do something completely wacky in a wacky market? But luckily in this case, we can kind of completely enumerate the number of states and figure out what the algorithm outputs were.
So I guess in some sense we should celebrate that the on-policy approaches did give you the optimal policy you were expecting, but then really begs the question to dig into, what about off-policy approaches do you think we're limiting there? Why couldn't the optimal policy be found under those conditions?
Yeah, we'll call it a draw, as the Black Knight says in Monty Python.
Yeah.
We'll call it a draw between the cynics of RL and the proponents. The big difference between the two is that for an on-policy learning algorithm, you need to have a realistic simulation of the environment so that you can evaluate what a policy looks like. And in real case settings, for various reasons, not least moral reasons, it's very difficult to do on-policy learning. Say if you're developing drugs, you couldn't morally give people an exhaustive number of molecules and kind of record all of the responses that they have. So in real life, off-policy learning is the thing that we have, because we don't have much of a choice. And also, depending on different areas of application, like economics, it's just impossible to run experiments. If you're a macroeconomist and you're trying to figure out certain kind of relationships between macro variables, you just have historical data. You don't have the luxury of being able to run experiments and see what the results were under different policies. You just get given what you get given, and then you have to try and make sense of the data. So you can't afford to give up on off-policy learning. And we've kind of got to understand why, for what reasons it would fail, and then kind of correct for those reasons. And that brings us on to the title of the paper. So Goodharts Law is an error, a cognitive error that is made so consistently by policymakers. It has its own name, it's well studied.
Yeah, could you give us a rough definition?
Yeah, sure. So there's a number of concepts that all came out in the kind of mid-70s. For one reason or another, Goodhart seems to have got the naming rights, although you could also call it Campbell's Law, and you could call it kind of similar to the Lucas critique. And there's also this thing called the Cobra Effect, which is kind of all tied in there. So Goodhart originally stated it in 1970 on the subject of monetary policy. He said that any observed regularity will tend to collapse when pressure is placed upon it for control purposes. So this was restated by an anthropologist called Marilyn Strathern in 1997. She said, when a measure becomes a target, it ceases to be a good measure. And then most recently in a paper by Mannheim and Garabrandt, 2018, they say Goodhart's Law is when optimization causes a collapse of the statistical relationship between a goal, which the optimizer intends, and the proxy used for that goal. So we can see that happens with the dog and his barometer. So his goal is to go outside with the right weather and the right coat. The proxy that he has is the barometer. That's the only thing he can observe. And he has this option to control that proxy. With the off-policy learning he does, and by controlling the proxy he destroys the causal relationship between the pressure and the barometer, and so he ends up doing this very stupid policy. So even if you are a big fan of RL and AI and a big champion of AI, you don't need to be upset by the result. In fact, I think it's a bit of a badge of honour that AI comes up with the same kind of results and same kind of errors humans come up with. And as computer science matures slightly and AI matures, the study of errors that AI makes is going to become a kind of subject area in itself, I think. There's hundreds of examples of Goodhart's Law, but I guess governments in particular are very, very guilty of falling foul of Goodhart's Law. I was trying to think of some kind of examples.
Well, one I go to a lot is imagine if a software company wanted to increase productivity and they started offering bonuses to the software engineers that wrote the most lines of code in a day. It seems unlikely that programmers in pursuit of that goal would also still deliver quality software. It's easy to write more lines.
Yes, exactly. That would be an example of an adversarial response. There's this thing called the Cobra Effect, which is related to Goodharts Law. It's an apocryphal story about a governor in India during the colonial times who, for some reason, decided that he didn't like cobras. So cobras are quite a dangerous snake that lives in India. So he introduced a bounty for cobras, and the enterprising locals promptly started breeding cobras to collect the bounty. And then the authorities eventually realised that, hey, we're getting a lot of cobras, kind of more than we expected, and they dug in a bit and they observed this adversarial response. They cut the bounty. Then the people who were farming the cobras no longer had an incentive to keep them anymore, so they just released them. So the end state was the state ended up with a lot more cobras than it began with, because there was an adversarial response to this incentive structure. And there's a few other examples of, strangely, it seems to crop up a lot with pests. So I think there was an example with colonial Vietnam, French governor deciding that they wanted to get rid of rats, so he paid a bounty on rats' tails, and people started breeding rats, chopping their tails off, collecting the bounty in the tail, and then releasing the tailless rat. So again, exactly the opposite happened from the policymaker.
Sure, despite the best of intentions. Well, I'm thinking of maybe a less adversarial case. What if, I'm a drive away from Las Vegas, all the casinos here in the U.S., if I thought that I had some button like this barometer I could push and it made me lucky at the roulette wheel, I might develop that false belief, but eventually I'm going to go broke. Why didn't the off-policy learning eventually learn its lesson?
Off-policy learning, it caches experience under all kinds of policies. So mixed in with the policy of pressing the barometer and receiving the disappointing reward, you also have the occasions when the barometer just happened to be high and going out without a coat was the right response. So the way that the data is stored at DQN, you don't store the history of actions, and you don't store the history of kind of previous variables. Remember, we modeled this as an MDP, so the assumption of MDPs is that the current state is kind of sufficient for you to be able to predict future states. So there's this mismodeling here, kind of misspecification, because actually it would be very useful to know whether we had press the barometer in previous periods. There is a deliberate misspecification here. So other approaches, I'm sure, would return the optimal policy. So if you do a partially observable MDP, or you were to start kind of expanding your state space to include full history, then I would expect the off-policy learning method to kind of work as you would expect it to work. But when you are modelling in real life, there are always going to be hidden variables, and you have to draw the line somewhere when you're kind of modelling up a problem. So the fact that this paper has a kind of deliberately mismodelled approach, as a cynic, you could say, well, that's why the off-policy learning method doesn't work. But as someone who's tried to kind of use RL in real life settings, I would say that you're always going to have an element of that. So the result, to know that using off-policy methods are less robust, and that if you had the choice, it'd be better to use a non-policy method. And I think that's a decent thing to know. On the subject of Goodharts Law, one example would be laptops for children. So it's been observed that the kids with laptops have better educational results. So a typical government response would be to say, well, look, there's this clear correlation between laptops and educational attainment, so let's buy them laptops. And I'm sure probably now, if you don't have access to, especially now during the lockdown, not having access to a laptop when you're meant to be learning would be a major hindrance. But there are confounding issues in there as well. So just being given a laptop isn't going to help you if you have no access to broadband. It just becomes a brick, I guess. So just by kind of dispensing laptops to everyone who doesn't have them is not going to necessarily recreate this relationship that you originally found, for a number of kind of confounding reasons. Another example would be, I think there's an observation that kids born earlier on in the academic year perform better than kids who've got summer kind of later on birthday. So I don't know in the US, but in the UK, the academic year runs from September through to September. So if you've kind of got an early birthday in your academic year, so September through to December, I think there's been some studies that show that you perform academically better than if you have a summer birthday, so May, June, July. So you can imagine an authoritarian government then saying, well, look at this. We need to mandate that everyone has their kids so that they're born between September and December. Everyone obediently obeys because it's a very powerful and convincing government. So all of a sudden, all the kids are born between September and December. But then the original kind of causal structure has been completely and utterly changed. So the observation that these earlier birthdays did better is just a result of them being kind of older when they're taught things. And then if everyone's exactly the same age, then the causal relationship would be completely destroyed. That could be an example of another Goodhart error, which might happen in a very controlling government situation.
That one is especially striking and problematic to me because if we accept the premise that at a young age, being 9 months older is a major leap, which seems very reasonable to me, then this government policy of saying let's have all the babies in 3 months actually would have leveled out the educational process, I presume, because that gap would disappear. So it technically worked, I guess, but just in an unnecessary or spurious way, perhaps.
I suppose it would even things out. As a parent, your child would no longer benefit over the other kids.
But half the students still would be in the bottom half of the class, so I don't know what we achieved.
Yeah. Another silly thing might be, I think there's been some work with people with surnames in the kind of first half of the alphabet. For various reasons, for various alphabetical ordering reasons, they seem to end up with higher salaries than people with surnames in the second half of the alphabet. So again, you can imagine everyone trying to change their name to Aardvark and things like that. But it's a response to a policy, and the response to the policy ends up changing whatever the causal structure was for the observation in the first place. This comes back to Pearl's big problem with machine learning, and Pearl has developed this thing which he calls the ladder of causation. So on the first level, the very simplest problems he thinks you can just solve by using correlations. The second rung is where you have to do interventions, you have to do experiments to try and understand what the causal structure of a problem is. And the third rung is counterfactual reasoning. So given that this thing happened, reasoning what would happen if something had changed. Counterfactual reasoning is quite an advanced thing that humans do naturally. But if you look at these three levels, you'll see that machine learning is on level 1, essentially. All the reasoning that machine learning does is correlation based. And so reinforcement learning, you would expect, should be on level 2, because it is, as I mentioned earlier, it should be very intimately tied up with the idea of experiments and acting and observing changes in the world according to the policies. But without an explicit treatment of causality, there's a fear that RL maybe hasn't got up to rung 2, maybe it's on rung 1.5. But this mantra amongst data scientists that data will tell you everything is actually wrong. This is a message that Pearl wants to get across. And Goodharts Law is a way of kind of illustrating that just observing data in itself isn't enough for certain questions. You need to try and understand what the causal structure that generated the data is in the first place for you to be able to develop answers to questions, and particularly when you're developing policies to problems.
The physics community has an expression, and it doesn't really apply in our context, but I'm going to use it anyway, and the expression is, shut up and compute. So I guess the antithesis to Judea Pearl's point of view might be, forget about all that, let's just give as much money as we can to the DeepMind team, and eventually there'll be some framework that just kind of sorts all this out in an emergent kind of way. What are your thoughts on that?
Well, I mean, this is one of the hypotheses that maybe we test in the paper without an explicit kind of treatment of causality. Does the dog learn a decent policy? The answer is 50% of the time it does, 50% of the time it doesn't. I think the problem is that as machine learning becomes more widespread and more accessible, and we have all of these tools, and all of this work was done on a kind of mid-range laptop with free software that I was able to access from home, it's very democratizing. But as ML kind of moves out into industrial private use without a careful understanding of what causality is, then we can make some massive bloopers, and kind of holding too much faith in it I think will end up in disaster for a number of people. And what machine learning profession hasn't really got to grips with yet is that this first level, when we were just analysing data as static observers, but now with the systems that we've put in place as a result of those observations, we're actually changing the data ourselves. So we can end up in situations where, as a result of our systems that we've implemented from the data that we've observed, we're starting to change the data. So we're having a normative effect on the data and the populations. The impact on the data itself isn't something that's modelled or taken into account of for any kind of supervised learning approach. And you can see that with social media and content suggestion algorithms. So they are trained using supervised learning to maximise click-through, and then they're deployed. But then the content that they suggest to the people in turn changes people's views and behaviour, and then the process is repeated again. So another supervised learning round of learning is done on the chain data and behaviour of people, which has already been changed by the first set. And you have this feedback mechanism.
And the content producers who are adjusting their headlines to suit these algorithms.
Yes. And I think we've seen already how this kind of pushes everything to very extreme levels, where people's behaviours are changed and maybe they only get certain types of content, and then the content produces, as you say, produce content to match the already adjusted preferences and behaviors of people. You have this causal effect of deploying a machine learning algorithm, which is kind of accidental. If you're just looking at it as a succession of supervised learning problems, you would never understand what you're doing is impacting the data, because it's not within unless you kind of wrap it up into a multi-period reinforcement learning problem. If you're just doing it period by period, it's very subtle, things change, but there's no option for you to kind of observe that.
So in some sense, it's a little disappointing that the deep QN technique couldn't find the optimal policy, but I like the paper in that it's a demonstration of this. So it's not so much saying that's a bad methodology, but a cautionary tale, I guess. With that in mind, do you have any advice for practitioners on how they can adopt methods or deploy the right policies, especially in cases when it's not a toy problem and it won't be so easy to see the failures of your model?
So one thing about this area of reinforcement learning, and I guess the most popular area of reinforcement learning, is that it is model-free. There's an idea that you can learn policy just by receiving rewards, this feedback. But what I would say is that it's much better to have a model of the problem that you want to solve. Forget about this model-free paradigm, because in real life, where there are complicated causal mechanisms and there are confounding variables which are unobservable, it's better for you to use your common sense and come up with a model. Doesn't matter if it's misspecified, but come up with a model first. Have an idea of what a sensible policy or what a sensible answer is. And then even if you have the model, you have a vague idea of the model, you can use a kind of model-based reinforcement learning to try and get yourself an optimal policy. So I would say the model-free data is king approach is going to get you into trouble. But if you have a kind of model of the world in mind, then that's going to be a lot safer approach to take.
Hal, thank you so much for coming on to share your expertise. Is there anywhere people can follow you online?
You can follow me on Twitter, Hal_Ashton. I don't really say much on there, but I will promote any papers that I've published recently.
Well, a good source then. Yeah, this is really interesting. Thanks again so much for coming on to take the time and share things.
Thank you very much.
That concludes this installment of Data Skeptic Consensus. Hal Ashton was our guest, Claudia Armbruster is our associate producer, Vanessa Burciaga does guest coordination, and I've been your host, Kyle Polich.